Hello everyone. We'll be starting a new topic today, and we will be doing entropy and entropy changes. And I feel this is one of the best topics in chemistry because you can easily get marks from these questions. They are not very tricky, and also the concepts are not very difficult to understand. Also, this is not a very large topic, so I think we might not even do more than 30 minutes of the lecture notes, and then we'll be solving questions. And yeah, I think that will be a good plan for this topic. Okay, now let's understand what does entropy mean. Now, the way we define it is that entropy can be thought of as the measure of the randomness or the disorder of the system. Now, what does this mean? What is the meaning of randomness or disorder? Now, in chemistry, when we talk about randomness or disorder, we are talking about the particles, like how random the particles are or how disordered the particles are. Now, we have three states of matter, right? We have a solid, a liquid, and a gas. So, let me show you what this means. When you have a solid, the particles are very close to each other. They are touching each other. When we have a liquid, those particles are slightly farther apart. So, there is some gaps over here. And when we have a gas, they are completely far apart. Now, which one of these three do you think is the most disordered? Which one has the most order and which one is the least order? We can see that because the solid, they are arranged together in a nice lattice structure. These ones are ordered. They have a fixed order. So in a solid, there is the most ordering, and in a gas, because they are moving freely, they are disordered. They are not stable, right? So the gas has the most disorder. So this one is most disorder. And we say that the higher the randomness or the more the disorder, the greater the entropy of the system is. So this one, the gas, has the most entropy. And why does it have the most entropy? Is because it's the most disordered or the most random. And liquid will just be in the middle. Right, now the next thing is, in entropy, we talk about two main things. And you have to understand the difference between these two. So the first one is the system, and the second one is the surroundings. Now, what's the meaning of a system and the surrounding? Let's say you have a reaction taking place. So maybe you have HCl reacting with sodium hydroxide to give you H2O plus NaCl, right? This is a normal acid-base reaction. Now, this reaction is usually carried out in a container, right? So you have some HCl liquid over here, and you will add that sodium hydroxide into this. Now, the particles and the reaction happening inside, this is called the system. The whatever happens inside and you can't really see it, this is called the system. So whatever is going on behind the scenes, the particles reacting to each other, all this is the system. And what will be the surroundings? The surroundings will be the liquid here, it will be the air, it will be anything which is surrounding it, maybe your hand, the solvents, the air, all of these are included in the surroundings. But the particle level details are in the system, right? So in fact, even this liquid over here is the surrounding because the liquid inside it is the particles. So all the inside part is the system, and whatever you can see or it's in the outside, this is called the surrounding. Okay, so this is the main difference between the system and the surroundings. Now I want you to understand one thing. Uh, every substance in this world, like every atom or molecule or particle, has a certain entropy value. So for example, when you talk about maybe NaCl, this thing has a certain entropy value. If you talk about a gas, maybe oxygen, this thing has a certain entropy value. If you talk about anything, basically, any substance, it has an entropy value. And as we know that gases have a higher entropy than solids and liquids, then you expect the gas to have more higher value than the solid or the liquid. For example, oxygen might have positive 200. This is just a random value, but the solid or the liquid will have less. For example, maybe solid might have plus 50. But the point is that as you go from solid to liquid to gas, the entropy keeps on increasing. And all of these entropies, they are given in joules per Kelvin per mole. So this is 200 joules per Kelvin per mole, which is written as K power negative 1 and mole power negative 1. So when you talk about the standard molar entropy, this is the entropy of 1 mole of a substance. Here we have 1 mole. in its standard states. And the standard state of oxygen, for example, is gas. The standard state for NaCl, for example, is solid. So every substance has a standard molar entropy value, and it's given in joules per Kelvin per mole. So now let's look at what happens when the temperature changes, or when you change a state from one state to another. Do you remember this graph? This graph is the normal temperature graph, whereby we are changing states. So at the start over here, we have 0 Kelvin, and 0 Kelvin is when the temperature is the lowest temperature, basically. So this one is 0 Kelvin, and here what we are doing is that we are slowly increasing the temperature of the substance. And obviously at 0 Kelvin over here, this thing will be a solid, and when you increase the temperature over here, it starts to melt slowly. When it reaches a certain point over here, this is when it starts to become a liquid, right? So for example, if you take water, what's the melting point of water? The melting point of water is 0 degrees centigrade, or 273 Kelvin, right? So when it reaches a certain temperature over here, this is 273 Kelvin, it will start to melt and become a liquid. Now remember what we said about the states, that gases have high entropy values, followed by liquids, followed by solids. So when you go from a solid to a liquid, are you increasing the entropy or are you decreasing it? You can see that you'll be increasing the entropy because you're increasing the randomness or the disorder of the system. For example, this normal solid will now be more dispersed or more random because it's now a liquid, so they are more separated, right? So you can see that the entropy value has been increased. Likewise, when you go from a liquid to a gas, then also the entropy value is increasing because now you are increasing the randomness of the system. So you have particles which are more further apart now, and that's how you interpret this. Okay, now let's go to another important part of this topic, which is what does entropy changes tell you about the feasibility of a reaction? We say that if the entropy change for a chemical or physical change is positive, then the change is feasible, which basically means that if you have a reaction and its entropy change is positive, then that reaction will occur, it will be feasible, right? So for example, let's take the same reaction which we did above, which is HCl plus NaOH gives you NaCl plus H2O. If the entropy change, the overall entropy change for this reaction is positive, then this reaction will proceed, it will be feasible. And the opposite of it is that it won't react. But if the entropy change is positive, then it reacts. If it's negative, then it doesn't react. And we say that entropy consists of two things. It has the system and it has the surroundings. So there are two things involved when you calculate the entropy change. And if we find out that the total entropy change of this reaction is greater than 0, that means that this reaction will occur and it is feasible. If we get that this answer that we got over here is less than 0, then this reaction will not occur. And why does this happen? This is because nature, the way it is, it always tries to increase the overall entropy of this world. Like, these chemicals, they prefer more to be disordered than to be ordered. And this is a very random thing about these things. But anything which is more disordered is actually more favored in the world than if it is ordered. It's like even when you make your bed, you feel very lazy to keep everything in order, to make the bed sheets, to arrange everything in proper manner, because it takes effort. And these chemicals are like us only. They don't want to take a lot of effort to order themselves. They will prefer if they are more disordered and more random. Okay, so here's a summary of what we discussed. If the number of moles of products is greater than that of reactants, then the entropy increases. Why does it happen? Because if you have more molecules, then you have more disorder, you have more randomness in the system. Also, if there is a gas produced in a reaction from a solid and a liquid, the entropy increases. Why does it increase again? Because if you have a gas being produced, the gas is more random and more disordered than a solid and a liquid. And in a gas phase reaction, first of all, what is a gas phase reaction? A gas phase reaction is a reaction which only involves gases. Okay, so you have reactants as gases and products as gases. In these kind of reactions, if the number of moles of a gas increase, then entropy increases. Let's look at an example of this third point here that we talked about. So let's take this reaction for example. This one is a gas phase reaction. Why? Because it has gases in both reactants and products only. Now, the reactants over here has 2 moles of this gas, and the products totally have 5 moles of the gas. You can see that the reaction is going from 2 moles of gas to 5 moles of gas. So this means that the entropy increases over here. How about this one? This one, in the reactants, there is 4 moles of gas, and here we have 2 moles of gas. So you have more order in the system, and so the entropy will decrease. Now let's actually start doing the calculation stuff. And how do you actually calculate these entropies, and how do you calculate if a reaction is feasible or not given values? And this is where most of the CIE past paper questions will come. Okay, now the general formula for the entropy change of a system is products minus reactants. So you take the total entropy of the products minus the total entropy of the reactants. But remember, we say that in entropy you have two things. You have the system and you have the surroundings. So we have the system and we have the surroundings. The formula for the system part is the total entropy of the products minus the total entropy of the reactants. But the total entropy has both. It has the system and it has the surroundings. If the total entropy change in a reaction is positive, then the reaction is feasible, else it is not feasible, and this is what we discussed above as well. Now you might be wondering what is the formula for the total entropy of the surroundings. For your syllabus and for your past paper questions, you don't even have to know this, but just in case you're interested in it, this is the negative delta H divided by T. This is the formula for entropy of the surroundings, but you won't be asked about this, so don't bother about this if you can't cram it. Now the challenge of using that equation is that it's actually very hard to get the entropy change of the surroundings. Like, to calculate this value is quite difficult. So what we do is that we use something called Gibbs free energy change. And what does this mean? Basically, this guy called Gibbs who invented this equation, and it removes the entropy change of surrounding from the system, and instead it uses the normal enthalpy change of the reaction, which we know we can find. It uses the temperature, which we have, and it uses the entropy change of the system, which we can also find. So this is the way to find out if a reaction is feasible or not. And this time it's the other way around. Remember, we said that if the total entropy is greater than 0, then this reaction will occur, and if it's less than 0, then it won't occur, right? But when we are dealing with Gibbs free energy change, this time it's a bit different. If the Gibbs free energy change is greater than 0, then the reaction is not feasible, it will not occur. And if the Gibbs free energy change is less than 0, that's when the reaction is feasible. And why is that? This is because you see in this reaction there's a negative introduced over here, and this negative changes the whole dynamics of the signs. Before we just had normal delta S, but now this negative is multiplied with the delta S, so that's why even the inequality changes. So if you get that the delta G is greater than 0, this means that the reaction is not feasible. But if the delta G is less than 0, then the reaction will occur and it's feasible. And this is very important actually. In your exams they will tell you that will the reaction be feasible or not, and why is that the case. And the way you answer this is by using the value of delta G. So you use these two inequalities to get your answer. One more thing I want you to understand is that if a reaction happens slowly, it doesn't mean that it's not feasible. Like, feasibility and rate of reaction are not the same things. You can have a reaction which is happening very, very slowly, but eventually it does happen. This is still called a feasible reaction. But there is some reaction which don't take place at all, right? For example, you can take a reaction like rusting. Some rusting processes takes a lot of time. It might even take 1 year, but it will eventually happen. So It might be slow, but eventually it does react. And there is some processes which... Now let's go to the last part of this topic, which is temperature changes and feasibility. And this is a very important part of this topic, and it's often the most confusing one. So let's try to pay the most attention to this. Now, let's assume that a reaction is exothermic. Okay, so let's assume that we have our HCl plus NaOH gives us NaCl plus H2O. Imagine that the delta H over here is negative. In fact, this reaction is a negative, has a negative delta H. So this delta H over here has a negative sign, right? Now, if you want this reaction to be feasible, what sign of delta S will you use? Will it be positive or negative? Let's take both scenarios, and we have to understand both scenarios. If delta S is positive over here, when you multiply a positive value with a negative value over here, you get a negative value. And so the overall results will be negative. Let's use example values to elaborate this. For example, this delta H is negative 100. So here we'll have negative 100 minus, let's assume T for now is 30 Kelvin. So I'll keep 30 over here. And let's say we have a delta S value of positive 10. You can see that the result that you get over here is negative 100 minus 300, which is negative 400. Which means that if you have a positive entropy value, your delta G is always less than 0 for a reaction which is exothermic. So let's write this. So I've written out what we just explained over here, that if the delta S is positive, then the Gibbs free energy change will be negative. And remember, we say that if the Gibbs free energy change is less than 0, then the reaction is feasible. Now let's look at the other scenario. So again, I'll just rewrite the formula. Delta H minus T delta S. We said that the delta H is exothermic, which is negative, and we have delta S over here. Now let's take the second scenario where delta S is negative as well. So this is negative. You can see here that we are multiplying a negative value with a negative value. So this value over here is now positive. And if this is a positive value, you have to minus this with the delta H. And so delta G can either be positive or negative, depending on which value is bigger. Again, let's use the example to explain this. We'll use delta H as negative 100, the same one. And we will use our temperature as 30, and we will use our entropy as negative 10 this time instead of positive 10. So this will be negative 100 minus 30 times negative 10. What do we get as the answer here? This will be negative 100, and when you multiply these two, you get plus 300. So you get the overall answer as positive 200. Hence, this means that the delta G over here is more than 0, and so the reaction is not feasible. But there is one way in which we can make this reaction feasible, and that way is to decrease this temperature value until the positive value is less than the negative value. Let me show you. So let's say we decrease the temperature of this reaction. Okay, so this will be negative 100, the same one, minus, let's make this value to be, for example, 5 instead of 30. So we have reduced the temperature of this reaction. And the same entropy value, negative 10. How much do we get this time? This time we get negative 50. So you can see that the values for delta G actually depend on the temperature value. If the temperature is low enough, then the reaction can be feasible. But if the temperature is high, then the reaction is most likely not feasible. So you can see this is what we explained over here, that if the delta S is negative, then the Gibbs free energy change can be positive or negative. But if the temperature value is low enough, then the reaction can be feasible. Right, that's it for this chapter. I hope you understood the core concepts of entropy, and these are the main things that you will be asked on in your exam. I don't think they can ask anything apart from this in your exam, so make sure you study this well. And next we will do past paper questions, around I think 4 or 5 of them. And if you solve those, you'll be very good to go in your past papers. Thank you for watching.